So now what I would like to do is talk about section 6.2. 6.2 talks about the number of elements in a finite set. One of the things that we're going to see is that we very often want to know how many elements are in a set. And I know at this point you're probably thinking, why are we even talking about this? But I assure you, once we get to probability, it will be extremely relevant. Okay? So, there's a formula that comes out of this section that's really quite important. But what I would like to do is motivate the formula for you, because I believe that formulas definitely take on more meaning when you understand why they are what they are and also where they came from. Okay? So, let's take this first scenario here. Okay? Suppose I have the sets A, and A is going to be 1, 2, 3. And suppose I have a set B, and B is also a set with 3 elements. It contains 4, 5, and 6. Granted, not very interesting sets, but that's fine. All right. Well, there's a few things we can do. We can find the union of these two sets, and we can also find the intersection of these two sets. So let's do it. If I want to take the union of A and B, again, union means put them together. So I claim it will just be 1, 2, 3, 4, 5, and 6. Okay? Now let's do the intersection of these two sets. In other words, where do they overlap? What do they have in common? And I think you'll grant me they don't have anything in common. So the intersection is the empty set. You may or may not recall the word we use for these two sets then is that they are disjoint. All right, so now what I'm going to do is I want to talk about the number of elements in various sets. That was a lot of writing to say the number of elements, okay? So again, we want to develop just some notation so it's easier to talk about this. So when, for example, I want to talk about the number of elements in set A, the way we write that is n of A. That's all we mean, is we just want to know the number of elements in A. All right, while we're on the subject, how many elements are in A? I think you'll grant me that there's 3. Let's talk about the number of elements in B. How many elements are in B? 3. All right, well, we've got 2 more sets listed here. We might as well count their elements as well. How many elements are in my union? Well, we can count them and we get 6. And do you also agree that the number of elements in my intersection is 0? All right, now this is kind of a neat little thing. Okay? When we talk about union, we're talking about putting things together. I think you'll grant me when we talk about numbers and we talk about putting them together, we're talking about addition. Okay? That's our operation. And look at this. Here's set A, here's set B. I put them together and got this union. And check it out. Will you guys agree that the number of elements in A union B is precisely the number in A plus the number in B? Look at that, right? We got 6 elements in the union, and I don't think we'll argue about the fact that 3 plus 3 is 6. Okay? That's pretty neat. All right, now let's take a couple more sets and let's analyze these guys to see what happens. Now what I will do is I'm going to have my set C be, how about 1, 2, and 3. And I'm going to have my set D be 3, 4, and 5. Okay? A union B, what we do is we put the sets together. Okay? Now, 3 is in both of those sets. You don't list him twice. You just need to list him once. So it's 1, 2, 3, 4, and 5. And in this case, I claim, oops, sorry, I'm so used to doing A and B. So this is C union D and C intersect D. All right, so I think you'll grant me in this case C and D are not disjoint sets. In fact, they overlap precisely with 3. All right, so let's ask ourselves if the same equality holds over here. In other words, I want to know, is the number of elements in C union D equal to the number in C plus the number in D? Well, is 5, I think you'll grant me there are 5 elements in this set, equal to 3 plus 3? And you're all thinking, nonsense. That's not the case. All right? So, what happened here that didn't happen in my previous example? What happened here is that these guys overlapped. So, what I'm going to do is I'm going to tweak this formula ever so slightly and say, okay, let's then subtract the number of elements in A intersect B. I think you'd agree that we still have equality because over here we're just subtracting 0. Let's see if that works over here. In other words, the number of elements in C union D equal to the number in C plus the number in D minus the number in the intersection? Well, there's 5 elements in C union D. There's 3 elements in C, 3 elements in D, and 1 element in my intersection. And sure enough, that worked. Okay? What this is called is my union rule for sets. Let me explain. Okay? So let me write this out. So our union rule for sets says the following. The number of elements in the union of 2 sets is the number in the first set plus the number in the second set minus the number in the intersection. Now, I think with the picture, you'll understand why we have to cross off the number in the intersection, okay? So, A union B is all of this, okay? Well, if I want to know how many elements are in A union B, yeah, the first thing I would do is count the number of elements in A. That's this region and this region, okay? And then I would add it to the number of elements in B, which is this region and that region. But you see, what happened is I double counted these elements in the intersection. Okay, I counted them when I counted the number of elements in A, and I counted them when I counted the number of elements in B. That is why we have to subtract off the number in the intersection so that we do not double count. Okay? So, that is our union rule for our sets. Now, we can do many examples where we can use such a rule. And I think that what we'll do is about 3 or 4 different examples here. All right then. So, my first example is the following. Okay, we're going to kind of take these in stages here. So this first example says, if the number of elements in A is 15, the number of elements in A intersect B is 5, and the number of elements in A union B is 30, what I want to know is how many elements are in B. All right, this is a straight up union rule question, okay? What we can do is take the information that's given and fill it in over here, okay? So I'm given that the number of elements in the union is 30. The number in A is 15. I want to know how many are in B. And the number of elements in the intersection is 5. All right, I can combine these two numbers here to simplify things. Would you agree on my right side? I can say, well, that's equal to the number of elements in B plus 10, 15 minus 5. All right, you guys, what plus 10 gives us 30? I think you'd agree that the number of elements in B is 20. All right, so the next one that I would like to do is the following. All right, here we go. So what I want to say is let's let A and B be subsets of a universal set U. Okay? And suppose we're told that the number of elements in our universe is 200. The number of elements in A is 100. The number in B is 80. And finally, the number in the intersection is 40. Okay? The first thing I want to do before we answer some questions is draw a Venn diagram. You guys, in this section, I just cannot emphasize it enough. You want to draw a Venn diagram. Okay? How will you know maybe on a test or a quiz to draw a Venn diagram? Because I'll tell you. All right, so let's fill in what we know. There's my universe, here's my set A, and there's my set B. Now, when you're filling in a Venn diagram, you always want to start with the innermost region first, okay? In other words, you want to start right here. I think you'll grant me that we can put 40 right there in the middle. All right, took care of that guy. Now, I'm given that the number of elements in A is 100. A is this whole circle. In other words, these two regions and these two regions need to add up to 100. Well, I've already accounted for 40 of them, so therefore 60 will go here. Okay? Next, the number of elements in B is 80. B is this entire region here, this entire circle. And that has to add up to 80. I've already accounted for 40 of them. Therefore, 40 is going to go here. Okay? Last but not least, I still need to know how many elements are outside here. These guys still live in my universe, they just don't happen to live in A or B. Okay? Well, remember, my universe has to add up to 200. Well, how many of the 200 have we accounted for? We've accounted for 140 of them. Therefore, I'm going to have 60 out here. Okay? That's the first step of what we're going to do here. Now that we have that, we might as well answer some questions that may or may not be very interesting. But let's do them regardless. Suppose I want to know how many elements are in B complement. Okay? Well, this is where the last section comes in handy. The first thing you need to ask yourself is, well, where is B complement? And remember, B complement is everything outside of B. So I'm going to cover up B. B complement then involves these two regions. Therefore, the number in them is the 60 plus 60, or 120. All right. What if I want to find the number of elements in, how about A complement intersect B? Again, we need to ask ourselves what region we're talking about, okay? A complement is everything outside of A, so it's that region and that region. And B, well, is this whole circle. Now, I'm looking at the intersection, so I'm asking where do I have a red X and a black X? And I think you'll grant me that my answer is right here. So the number in there is 40. All right, so what I would like to do now is a word problem. Okay. Actually, we'll do 2 word problems. So the first word problem, and I never grant you that any of the word problems we do are very interesting, but we will do them. So this one is called a sports club survey. And what this says is in a survey of 200 members of a local sports club, 100 members indicated that they plan to attend the next Summer Olympic Games. So 100 plan to go to the Summer Games. 60 indicated that they plan on going to the Winter Games. And 40 indicated that they plan to attend both games. And the questions that we want to answer are the following. How many members plan to attend? Okay, part A will say none of the games. Part B, how about summer only? Part C, how about exactly one of the 2 games? And then part D, at least one of the 2 games. Okay, before we even look and think about answering those 4 questions, let's draw a Venn diagram and fill in our circles, okay? So in this case, our universe consists of the 200 members of this sports club, okay? I'm going to call S for people who plan to go to summer games, and W for those who plan on going to the Winter Games. Again, we want to start with the innermost region first. Okay? So 40 goes smack dab in the middle because 40 people plan on going to both games. Next, we have 60 people who plan on going to Winter Games. We've already accounted for 40, therefore 20 go here. Next, a total of 100 people plan on going to the Summer Games. We've accounted for 40, therefore 60 will go here. Now, again, we still need to get this number out here because presumably not everybody's planning on attending the Olympics. Well, we've accounted for 120 of the 200 members. So I claim that 80 will go out here. Okay, that's the first step. Our next step is to answer these questions. All right, so first off, how many plan to attend none? We filled that out, 80. How many plan on going to the Summer Games only? Well, this is all of the Summer Games. These guys also plan on going to the winter ones. So summer only is just this region of your circle. Therefore, it's 60. All right. Now we're getting into some verbiage that's going to come up a fair amount. exactly versus at least or at most, okay? So exactly one of the two games means that they're going to summer only or winter only, okay? See, these guys are going to exactly one of the two games. So this is certainly a number we're interested in. This number we're not interested in because they're going to two games. This number we're not interested in because they're going to none. But these guys are also going to exactly one of the two games. So we'd add that 20, and so we would say that 80 people are going to exactly one of the two games. Last but not least, we want to talk about how many people are going to at least one of the two games. Now, when you say at least something, what you're talking about is that amount or greater. So if I'm at least 10 years old, I'm 10 or older. Okay? So in this scenario, at least one of the two games means they're going to one game or two games. And I claim that's precisely my union here. These guys are going to one game, therefore they're relevant. These guys are going to two games, therefore they're relevant. And again, those guys are going to one game, so they're relevant as well. So our answer there is 120. All right, I would like to do one more example that's just a slight bit different. So let's do it. All right. We're talking about newspaper subscribers. And it says that we're looking at a survey of 1,000 subscribers to a newspaper. So my universe is consisting of all subscribers. And what this revealed is that 900 people subscribe to the daily morning edition. $500 subscribe to both the daily morning and the Sunday edition. And the two questions that are being asked are the following. How many subscribe to the Sunday edition? And the next question is how many subscribe to the Sunday edition only? In other words, just the Sunday edition, not the daily morning edition. All right. Now, I said this one's a little bit different, and let me show you why. Okay? Whenever we draw Venn diagrams, we draw our box. Okay? That's our universe. So, what do we have here? We've got the daily morning people, and those are our Sunday people. All right. Well, we're given that 500 subscribe to both. So, we have 500 smack dab in the middle here. All righty. The next piece of information we're given is that 900 people subscribe to the daily morning. The daily morning is this entire circle. Again, we've accounted for 500 of those 900. Therefore, 400 will go here. Okay? Now notice, we're only given one more number here, the 1,000. But technically, we have two regions. The thing that makes this problem a slight bit different than the last one is there's nobody out here. Okay? The reason why there's nobody out here is because our universe is just consisting of subscribers. And these people out here don't subscribe. All right? So, we can then use that last number to say, hey, all this has to add up to 1,000. We've got 900. Therefore, 100 has to go here. So now let's answer those two questions. How many subscribe to the Sunday edition? Well, the Sunday edition is this entire circle right here. So we get 600 people. Now the next question is, how many subscribe only to the Sunday edition? Okay, this whole circle is Sunday, but now we're not interested in the people who also subscribe to the daily morning. Therefore, our answer here is simply 100. All right, so in the book, you'll see that there are some examples where you have 3 circle Venn diagrams, but we're not going to be headed there. So that concludes section 6.2. Thank you.